Okay, so death. It's the one thing we all know is coming, right? But what happens after? Well, that part is often wrapped up in mystery, maybe even a little bit of fear. But what if we strip all that away? What if we just look at it for what it is? A totally fascinating biological transformation. A predictable, natural process governed by chemistry and the environment. Let's dive in.
So what really happens after we die? I mean, it's a question everyone asks. From the second the heart stops beating, our bodies start this incredible journey of, well, returning to their most basic parts. And we're going to follow that journey step by step using the hard science of forensics.
All right, here's the plan. We're going to start with those first few hours, the stuff forensic experts get really excited about. Then we'll dive into the 4 main stages of decomposition. We'll even look at some wild situations where a body can be preserved instead. Then we'll see how things like temperature and location change the whole timeline. And finally, we'll talk about what all this means for us today in the modern world.
Okay, let's get into it. The moment life ends, a whole cascade of physical and chemical changes kicks off. And here's the cool part. They don't all happen at once. They happen in a super predictable sequence, almost like a story, if you know how to read the signs. So this timeline, it's like a clock for forensic investigators. It gives them a ton of clues about the time of death. First up, you've got pallor mortis. That's just a fancy way of saying the body goes pale because the blood stops circulating. Then comes livor mortis, which is when gravity takes over and pulls the blood down, causing these purplish stains on whatever part of the body is lowest. And then the one everyone's heard of, rigor mortis. That's when the body starts to get stiff.
So what is rigor mortis really? It sounds kind of spooky, but it's pure biochemistry. Think of it this way. While we're alive, this little molecule called ATP acts like a key. It unlocks our muscle fibers and lets them relax. But when we die, our bodies stop making ATP. No more keys. So the muscle fibers get stuck in this locked, contracted state. That's it. No mystery, just chemistry.
All right, after those initial changes, the main event gets started. And that's putrefaction. This is where the real transformation happens. And what's wild is that it's not driven by anything from the outside. It's powered by the trillions of bacteria that have been living inside our gut our whole lives. So this whole process unfolds in 4 distinct stages, and they have these surprisingly, poetic-sounding names. We're going to walk through each one. First, the chromatic, or color phase, then the emphysematous, which is all about gas, the colliquative, or liquid phase, and finally the reductive phase, which is pretty much what it sounds like.
Okay, phase 1. The first sign you can actually see usually shows up after about a day or 2. It's this greenish spot on the lower right side of the abdomen. And you might be wondering, why right there? Well, it's because that spot is right over a part of your large intestine called the cecum, which is just jam-packed with bacteria. Those bacteria start reacting with the hemoglobin in your blood, and boom, you get this new compound, sulfohemoglobin, which has that greenish color. It's literally the first brushstroke of decomposition.
All right, now things get, well, dramatic. This is the emphysematous phase. The bacteria basically go into overdrive, producing a ton of gas. We're talking methane, hydrogen sulfide, you name it. All that gas has to go somewhere, so the body bloats up, sometimes incredibly so. The pressure builds and builds, causing the eyes and tongue to protrude. And here's a really strange detail. Sometimes that escaping gas can pass through the vocal cords, making it sound like the body is groaning. Super unnerving, but again, it's just physics.
And of course, all this bacterial action creates a very particular smell. But it's not just a random odor, it's specific chemistry at work. When amino acids break down, they create these compounds. And you can see 2 of the main culprits right here, putrescine and cadaveric. I mean, you gotta admit, they're perfectly named, right? They're a huge part of what gives decomposition its signature scent.
So the last 2 phases kind of wrap everything up. In the colliquative phase, think liquefaction. All that pressure that built up gets released, and the body's tissues really start to break down and liquefy. This whole part can take months. And then over the next few years, the reductive phase takes over, and that's when all the soft tissues finally disappear, until at the end of the day, only the skeleton is left.
But wait, putrefaction isn't always the end of the story. It turns out, under some very specific, very particular environmental conditions, that whole process can just stop. It can be halted in its tracks, leading not to decay, but to preservation.
It really all comes down to the environment. The environment is the deciding factor. So, putrefaction, that's the default setting, what happens in most places. But if you're in a really wet, oxygen-poor environment, the body's fat can transform into this waxy, soap-like stuff called adipocere. Super weird. On the flip side, in an extremely dry, windy place, the body can just dry out and mummify. And then there's this other one, scarification, which can happen in sealed metal coffins. It essentially tans the skin, making it feel like leather.
Of course, when we think of preservation, we usually think of the artificial kind, right? Like the incredible mummification techniques of the ancient Egyptians. And while they were obviously doing it on purpose, the science behind it is exactly the same as natural mummification. You just have to get rid of the moisture to stop the bacteria from doing their thing.
So yeah, it's super clear that the environment is king. But it doesn't just decide if a body decomposes, it also dictates how fast. The timeline for all these processes we've been talking about can vary wildly.
Check out this quote. It's from way back in 1888, and it's a classic rule of thumb in forensics called Casper's Law. Basically, it says that if the temperature is the same, a body exposed to the open air will decompose twice as fast as one in water, and a whopping 8 times faster than one that's buried. It's such a simple but really powerful way to understand how exposure just hits the fast-forward button on the whole process.
Okay, so now let's pull this whole scientific journey into the 21st century, because that natural process we've just laid out, well, it's often completely interrupted by our modern funeral practices. And that, it turns out, comes with a pretty big environmental price tag.
Just take a look at traditional burials. The numbers are just mind-boggling. In the United States alone, every single year, we bury more than 13,000 tons of steel in the form of coffins. Think about that. That's an enormous amount of raw material just being put into the ground.
And it's not just the metal, it's the chemicals too. Embalming relies on fluids that are based on formaldehyde, which we know is a carcinogen. And every year we bury millions of gallons of this stuff right into the soil.
So, what does this all add up to in terms of a carbon footprint? A study in France broke it down, and the results are pretty eye-opening. A traditional burial can account for something like 11% of an average person's annual carbon emissions. Now, cremation is lower. Yeah, it's around 3%, but it's not zero. It still takes a massive amount of energy and releases its own pollutants into the atmosphere.
So what's the most eco-friendly way to go? Well, it would be something called direct inhumation. That's really just burying a body in a simple, biodegradable shroud and letting nature do its thing, letting all those processes we've talked about happen naturally. The big catch, though, is that this isn't even legal in a lot of places. Many countries and states have laws that require sealed caskets or concrete vaults in the ground.
And you know, that really leaves us with a final, pretty profound question. What started as a purely biological event has now become a real environmental choice. Understanding the science of what happens after we die, it's not just about morbid curiosity. It actually forces us to think about the legacy we're leaving behind, right down to our very atoms. So what will your final footprint be?